When you think about making a set of complete dentures, it's easy to just picture making new teeth. But it's so much more than that. It's a fascinating puzzle that sits right at the crossroads of biology, physics, and, believe it or not, art. We're talking about building a functional machine that has to work in perfect sync with the human body. So let's break down how this incredible feat is actually pulled off. See, when a person loses all their teeth, they're not just losing their smile, they're losing an entire biomechanical system. Your natural teeth are anchored deep in bone, giving them just incredible stability. A complete denture, though, well, that has to sit on soft, movable gum tissue. So the real challenge, the fundamental problem, isn't just replacing what's gone, it's about engineering a replacement that won't rock or slip or fall out. It is all about stability. All right, so here's our game plan. To really get how this puzzle is solved, we're going to walk through the whole process. We'll start with the challenge itself, then we'll look at how dentists build the perfect foundation, how they map the jaw's unique blueprint, and then how they engineer the bite. And finally, we'll see how it all comes together to create so much more than just a smile. Okay, let's really dive into that central puzzle. How in the world do you make a single solid object, the denture, stay stable on a soft, squishy, movable base? It's tricky because unlike our natural teeth, which all have their own roots, all the teeth in a denture are fused to one acrylic base. They have to act as a single unit. So any weird force on one side can tip the whole thing. And here's a detail that really drives home the challenge. With your natural teeth, when you slide your jaw forward, your back teeth usually separate a little bit. It's a normal thing called Christensen's phenomenon. But for a complete denture, that same little gap would be an absolute disaster. It would create a tipping point, pushing the front of the denture down and lifting the back right off the roof of the mouth. The seal breaks, and boom, all stability is gone.
So, if that's the problem, where do we even begin to find a solution? Well, just like building a house, it all starts with a perfect foundation. In prosthodontics, that's the field of dentistry that focuses on replacing missing teeth, that foundation is the impression. It's an incredibly precise mold of the patient's jaw. And I gotta tell you, getting it right is just as much an art as it is a science.
And getting this foundation right, it's been a challenge dentists have been working on for well over 150 years. You can see the evolution right here. From really early plaster in the 1840s to new techniques in the 1900s that tried to capture the mouth in motion. The goal, though, has always been the same. Get a perfectly accurate map of all the tissues. This brings us to what's pretty much the most widely accepted theory today, the selective pressure concept. It's a really clever idea. Instead of just pressing down equally everywhere, the impression is designed to put pressure only on the parts of the jaw that are dense and strong enough to handle chewing forces, while taking pressure off the sensitive areas. It's all about an intelligent distribution of force. Now, this number, 24 square centimeters, brilliantly shows why lower dentures are so much tougher to get right. The upper jaw gives you about 24 square centimeters of surface area to work with. That's your support. But then look at the lower jaw. It's only about 14. That much smaller foundation makes getting stability a massive, massive challenge. Okay, so the foundation is laid, but now we have a whole new problem. Where, in three-dimensional space, does the lower jaw actually line up with the upper one? Without any teeth there to guide the bite, we need a reliable reference point. We need a blueprint. And this is the million-dollar question. I mean, think about it. When you have teeth, they just naturally guide your jaw into place. They dictate how everything meets. But when they're gone, you can't rely on that tooth-to-tooth relationship anymore. You need something more fundamental, something that doesn't change even when the teeth are gone. And the answer is this incredible concept called centric relation. This is a bone-to-bone relationship. It's the position where the ends of your lower jaw, the condyles, are seated comfortably in their most upward and forward position within your jaw joint. This spot is determined by your ligaments and muscles. It's stable, and most importantly, it's repeatable. It's like the jaw's true home base. This diagram shows you exactly what we're talking about. Look at the joint itself, the TMJ. Centric relation is defined by the position of that condyle inside the fossa, resting against the little disc. It has absolutely nothing to do with teeth. This pure anatomical landmark is what allows a dentist to completely rebuild a person's bite from scratch. So, how on earth do you find this exact point on a patient? Well, one classic method is this really clever graphic tracing. You put a tiny little stylus on the upper rim, and as the patient moves their jaw left, right, forward, and back, it literally draws the outer limits of their jaw movement onto a plate on the lower rim. And this is what you get. What you see in diagram C is often called a Gothic arch tracing. It creates this really distinct diamond or arrow point shape. And that sharpest point at the very tip, labeled CR, that is the most stable, repeatable position the jaw can get into. That is centric relation. We just found our blueprint. So let's recap. We have our foundation from the impression. We have our blueprint from that centric relation record. Now it's time for the really cool part. We have to engineer the bite itself, the way the teeth come together, to make sure it's not just pretty, but perfectly stable when it's in motion. Now this is maybe one of the most important takeaways. The rules for how denture teeth should work are the exact opposite of the rules for natural teeth. Remember how natural teeth are designed to separate in the back? Well, denture teeth have to do the opposite. They must maintain contact on both sides at all times during all movements. This is what we call balanced occlusion, and it's the secret sauce that prevents the denture from tipping over. Achieving this perfect balance is kind of like solving a complex physics equation with 5 key variables. It's known as Haneku's quint. You've got factors like the angle of the jaw joint and the steepness of the teeth, and they're all interconnected. If you change one, you have to adjust the others to keep the whole system in harmony. And here's the heart of the engineering challenge. One of those 5 factors, the condylar guidance, is just the path the patient's own jaw joint follows. That's fixed. It's their anatomy. The dentist can't change it. So what they have to do is record that value and then scientifically and artistically adjust the other 4 factors, things like the angle of the front teeth and the curve of the bite, to solve the equation and create a perfectly stable result. Okay, let's bring it all home now. We've seen how these 3 core pieces, the foundation, the blueprint, and the engineered bite, are meticulously put together, all to solve that initial problem of instability. You see, it's not really 3 separate steps. It's more like 3 pillars that support the entire structure. A perfect impression creates that stable foundation. A precise centric relation record gives you the correct blueprint for building. And an engineered, balanced bite makes sure the final product stays stable when you're actually using it. When all 3 are done right, you get a denture that actually works. And this quote from the famous prosthodontist, M.M. Davin, it just perfectly captures the real goal here. The point isn't just about filling a space with plastic teeth. It's about designing a prosthesis that preserves the health of the bone and tissues that are still there for as long as possible. And that kind of leaves us with a final thought, doesn't it? When you really break it all down, creating a complete denture is this incredible act of personalized bioengineering. It really makes you wonder, what other fields out there require such an intimate blend of biology, physics, and art, all to restore something as fundamental as our ability to eat, speak, and smile with confidence?